I'm Kim Newton from the Office of Communications at NASA headquarters. I'd like to welcome everyone to the Low-Density Supersonic Decelerator, LDSD, overview briefing today, including our friends from the media. I'd like to start out by introducing our panel participants. Starting to my left, we have Captain Bruce Hay. Captain Hay is the U.S. Navy Commanding Officer of the Pacific Missile Range Facility here in Kauai. To his left is Steve Jerzyk. Steve is the Associate Administrator for the Space Technology Mission Directorate at NASA headquarters in Washington. To Steve's left is Dr. Ian Clark. Ian is the Principal Investigator for the Low-Density Supersonic Decelerator at the NASA's Jet Propulsion Laboratory in Pasadena, California. And next to Ian is Dr. Mark Adler. Mark is the Program Manager for the Low-Density Supersonic Decelerator, also at NASA's Jet Propulsion Laboratory in Pasadena, California. We'll hear some opening remarks from our panel members. Then we'll take questions from reporters in the audience. Next, we'll take reporters joining us on the telephone. Please enter *1 to get into the Q&A queue. We'll also take questions from our Ustream followers using the chat box and Twitter using the hashtag AskNASA. Now I'll turn it over to Captain Hay.
Well, thank you, and good morning from Kauai and the world's largest instrumented training and test range. We're thrilled to be supporting NASA again this year for the Low-Density Supersonic Decelerator. It was an amazing test last year, and we're looking forward to hosting them again next year. So you're not here to see me. I'll gladly turn it over to the professionals to my left. Thank you.
Good morning or good afternoon, everyone, depending on where you are. And first, before I get started, I want to thank Captain Hay and his team here at PMRF. We couldn't have done last year's flight test, obviously, without them, and we couldn't pull off this test coming up without the great support that we get from his team here. So thank you, Captain Hay. We learned a great deal from last year's flight test and used that knowledge to improve the design and manufacturing of the hardware to enhance its strength and performance. So this year, I'm cautiously optimistic that we'll have a fully successful flight test. But either way, we're going to gain a tremendous amount of knowledge. Before I turn things over to Ian and Mark, who'll give you the details of the flight test, I want to take a moment to talk about how important developing and testing technologies like we're doing here is to NASA. Technology drives exploration and our journey to Mars, and that's why we develop new technologies, demonstrate them on the ground, and then eventually fly them. We have to fly them to prove them out and to enable the future agency missions, both in science and in human exploration. NASA's Space Technology Mission Directorate is sponsoring this project, as well as many other technology projects, developing critical capabilities that are needed, again, for the future. Our current and planned investments address high priority challenges in achieving safe and affordable deep space exploration. In fact, over the next 18 months, we're going to be launching approximately 6 flight demonstration missions. Right now, we are kind of at the technological limits of what we can land on Mars in terms of size and weight. We landed about 1 metric ton. The Curiosity for the MSL, or Curiosity rover, it was about the size of a Mini Cooper and about 1 metric ton or 2,200 pounds. And that's about all we can do with the current technology that we use, which actually goes back to the 60s and 70s and is derived from the Viking missions, which landed on Mars in '76. So this new technology is required to land 5 metric tons for human missions, maybe 30 and beyond metric tons to the surface. So the parachute we're using today can improve performance, landed mass by 100 to 200%, and that's really critical for not only future enhanced robotic missions, but human exploration of Mars. As I mentioned earlier, STMD will launch 6 additional technology demonstrations. A couple of those are Deep Space Atomic Clock to improve deep space navigation, and Green Propellant Infusion mission, which is going to develop a higher performance, non-toxic propellant to reduce processing time and cost, as well as provide higher performance in space propulsion. Since the formation of the National Advisory Committee on Aeronautics, or NACA, in 1915, we've done experiments like this to expand humanity's knowledge in air and space travel. As was the case with those early pioneers of flight, there's no guarantee that these tests will be completely successful. That's why we go and fly. They're flight experiments. But I'm confident, again, we will learn a great deal from the test and gain a lot of knowledge that will shape future tests and future systems to land larger payloads on the surface of Mars. NASA could be ready for using this technology in future landed Mars missions as early as the 2020s. And it could be especially beneficial for missions like Mars sample return and for human exploration precursor missions. NASA's Space Technology Mission Director is making significant and real progress in addressing many of the challenges for achieving safe and affordable deep space exploration. Again, technology drives exploration and our journey to Mars, and developing the technologies that will enable future exploration of the solar system and beyond. And this is just one example of that. Really looking forward to flying this week, hopefully. Cross our fingers if the weather will cooperate. And now I'd like to turn it over to Dr. Clark, who's going to tell us more about the flight test and the technology. Thanks.
Thank you, Steve. Give you a little bit of background. 1,000 years ago, the explorers from this planet and the technologies that drove their exploration across the expanses of ocean and helped bring the first inhabitants to this island relied on technologies like using the stars for navigation and using the wind to carry them across the ocean. Today, as we cast our eyes from this land of red sand to another place of red sand, the planet Mars, we continue to rely on a lot of those same technologies. Our spacecraft still use stars to navigate across the expanses of space. We still rely on wind not to carry us across the space, but to help slow us down when we arrive at Mars. Our spacecraft enter the atmosphere going 10,000 miles an hour, and it's the oncoming wind and large aerodynamic drag devices that help produce the drag to slow us down to safely land us, on the surface of Mars. So a few years ago, we landed the Curiosity rover. This was the last of the past 7 successful missions we've had to Mars. And even before we landed Curiosity, we started to realize that the technologies that we had to land robotic missions to the surface of Mars were essentially saturated. As we started thinking about the next generation of more capable, more exciting, more bold missions to Mars, we started realizing that we didn't have the technologies in place to land them. And we had to start today to start developing those technologies. Things like inflatable drag devices that we can inflate at several times the speed of sound, and a new supersonic parachute, 100 feet in diameter. Those are the technologies that LDSD is developing to enable those future generations of Mars missions. They'll allow more mass to the surface of Mars, and they'll also allow us to access more surface itself, to regions of Mars that we haven't had available to us in the past. And so, for example, if we go to the first image here, the colored spots denote the areas where we could land something like the Curiosity rover, a 1-ton rover. And each of those X's are places and locations that we've landed previous missions. All of the region that's shaded in black are elevations that are too high. That is, there's not enough atmosphere to slow us down if we were to try to land at some of these higher elevations. With the technologies that LDSD is developing, something like the Curiosity rover, we'd be able to open up nearly the entire surface of Mars. We'd expose much of the southern hemisphere and large regions of the northern hemisphere as well. But if we started thinking about the next generation of missions, we know that those are even more massive. If we go to the next slide, if we tried to rely on the technologies we had today to land those missions, that would be 2 to 3 times heavier than the Curiosity rover. The graphic in the upper half shows where we could do that. It's largely entirely black. There's actually a very small region of purple. If you squint and hold a magnifying glass up to your television, maybe you can see. But with the LDSD technologies, the inflatable drag devices, and the new parachute, we can open up at least half of Mars to these increased mass payloads. We can go back to a lot of the same places with these more capable missions and more capable instruments. And we start to open up regions of Mars for human precursor missions as well. So last year, we came here and we got to conduct what was a phenomenally successful shakeout test of a test architecture that we had put together just to test these technologies. And so I've got some data from that I can show a video. If we cue the first video. So we have this test vehicle, and Mark's going to talk a lot in a moment about how we conduct the test. But just take for granted we're going 4 times the speed of sound, and we got to inflate our SIAD device, an inflatable drag device. We got to do this all a year ahead of schedule. Again, last year was really just a shakeout test. We got lucky in the sense that the technologies were ready. We got data a year ahead of schedule. So we saw the SIAD inflate phenomenally, uniformly. We saw very little disturbance to the vehicle during the inflation process. And we got a ton of great aerodynamic data and aerothermodynamic data, and we saw the SIAD perform better than we even expected. If you cue the next video, we also got early tests of another device we've had to develop just to deploy our large supersonic parachute. And go ahead and press play. So here we're going about 2.8 times the speed of sound. We shoot out the back of the vehicle this large 15-foot diameter balloon parachute device that helps pull a parachute off the back. And then we tried to take a 100-foot parachute and inflate it into 2,000 mile an hour wind and see what happens. Now, the data treasure trove that we got from that test has been tremendous. Orders of magnitude better quality and better quantity than anything we've ever had. We've been using supersonic parachutes for over 40 years, and our understanding of them really stems from a few tests that were conducted in the 1960s and the 1970s. And the data from that test exists in a few technical reports and in a few grainy 16mm videos. We've digitized those. I've personally watched each one of them probably hundreds of times as they're trying to glean more and more information about the nature of these devices, how they inflate, how they operate, how they behave. And we've got images like, if we cue this still right here, you see these are images from some 1960s and early 1970s tests. Generally, we see the parachute inflate. We get some understanding of the behavior. Now, if I compare that to the data set we got last year, just in the quality of the image, go to the next image, please. We saw things that we had never seen or imagined existed before. We saw a much more dynamic and much more turbulent parachute inflation than we thought we had ever known. We saw things like the suspension lines exploding like lightning and moving in a very chaotic manner all over the place. We could resolve the individual suspension lines themselves. Even though the parachute's nearly 200 feet away from us, we could see the suspension lines that are 1/8 of an inch in diameter, and we could count nearly every single 91 of 96 of them. We could see where they interfaced with the parachute. We could see the individual fabric. We could see where the fabric seams were, and we could start to see things in the nature of the inflation that we had never known before. In fact, when we showed some of these videos to folks who had been working on parachutes for 40 years, they immediately thought this was the worst parachute inflation they'd ever seen. Then we started watching the old videos again and going back and seeing those, and we started realizing that those behaviors existed previously. We just didn't know what to look for. We didn't have this this data set available to us, this understanding. And so we've started learning a lot. If I go to the next slide, you can even get a comparison from 40 years ago imagery in our data set to what we've got today. If I were to look at the image on the left, if somebody showed me that and didn't give me any context, I'd probably ask why I was looking at a ball of cotton or a cotton plant. And now I've got the image on the right to start to glean a much better understanding of the physical processes that govern and dominate how these parachutes behave under these 2,000-mile-an-hour winds. We have made a number of improvements to our parachute. Again, we got all this data. We've improved our understanding by an order of magnitude of supersonic parachutes. And so we've got a new parachute that we're testing this year. If we go to this slide. We fundamentally changed both how we design and analyze a parachute, but the parachute design itself that we're testing is new. We've got a more curvature to the geometry that helps to reduce the stresses early on in the inflation process. We've added a lot more structural, high-strength material in the crown of the parachute and throughout the parachute to make it more robust to a lot of the dynamics that we saw during the inflation process. We've got a lot of damage-tolerant capability such that if part of the fabric begins to tear, it won't propagate through the rest of the parachute. Overall, it's a much stronger, much more robust parachute that we think is going to provide another tremendous data set for us and hopefully perform very well for us under these conditions. So to describe a little bit about how we get the technologies to the conditions, I'll pass it to Mark.
So we can go to the next slide. You can advance to the slide showing the side and the parachute. So this shows the two technologies that we're going to be testing. As Ian said, we had a shakeout flight last year. We actually tested our vehicle to make sure we could get these technologies to the right conditions. We were in fact able to test the SIAD. That's that donut-looking thing that Ian is standing in the middle of. You can see him with his outstretched arms. It's about 20 feet in diameter. It is used to increase the diameter of the vehicle from 15 feet to 20 feet very rapidly at Mach 4. And we were able to test it last year, fortunately, and so in fact we now have that technology qualified for use at Mars. That's the first of two stages that we need of deceleration to slow down these very heavy payloads at Mars. The second stage is the parachute you see there. It's not to the same scale. It's a very large parachute. It is 100 feet in diameter if it's laid out on the ground, and you can see our 15-foot test vehicle hanging there at the bottom of it. That technology is now a new parachute that we developed this year since, again, last year we were able to get an advanced test in. We were able to see things about the parachute that didn't behave as we expected. We saw the parachute get destroyed in the test. Now we've developed a much more robust, more stronger parachute that we're going to be able to test this time. So let me go on to the next slide and show you how we tested this parachute on the ground before we flew it, before we're going to fly it this week in the upper atmosphere. This is at the Naval Air Weapons Station in China Lake, California, another Navy base that we use for doing our testing. It's a 4-mile-long rocket sled track. It's a railroad track that rockets go on. We carry up the parachute on a helicopter and drop it out of the helicopter. The parachute inflates, as you see there. And then once a large bullet goes into that funnel that you see right there, you see it coming down. As soon as that latches in, the rockets fire. And the rockets pull on that rope through a pulley, pulling the parachute straight down with over 100,000 pounds of force. This parachute was supposed to survive to 80,000 pounds. It survived to 120,000 pounds. And so we've shown that it has the strength it needs to survive the loads we'll experience at Mars in the full open configuration. We're now going to be testing it in the upper atmosphere here over Kauai, where we can actually simulate the thin air of Mars with the thin air of the stratosphere above our heads here. Do that at supersonic speeds, test the parachute at high speeds, and see how it behaves not just in the fully open configuration, but as it inflates. As you saw last time, the inflation was very complicated, so now we're going to see how it inflates in the supersonic flow in the test that we're going to do this week or next. So let's go ahead and run this one. This is a little advanced view of a technology that we're going to be developing more over the next several months. This is another SIAD. It's like the 20-foot diameter side, but this one is 26 feet in diameter. It's a much larger side, but it's actually not much heavier, so it's a much more advanced technology. It's more efficient. And this shows a rocket sled test, again at the same facility at China Lake, at slow motion, where we deploy the SIAD from a test vehicle at 250 miles an hour to simulate the flow of and the loads that it'll experience at Mars. There it is at full speed going over the camera, which then, of course, gets knocked over by the rocket sled. So that was actually a very successful test, and we showed for the first time that we can build this very large side, and it stays inflated and inflates down the track. And so we're hoping, Steve, to actually test that supersonically in the future. So next slide. Actually, we have now this model here, so I'll explain to you a little bit about our test vehicle and how we fly it. We loft it up on a balloon, and I'll show you what the overall profile is of the flight. Once we get it up there, we use this solid rocket motor in the middle here called a Star 48. It's a very powerful solid rocket motor that accelerates it from 0 to Mach 4 in a little over a minute. And is then flying through the air in about this direction. We call this a flying saucer, but it doesn't spin around or fly like this. It flies into the wind directly, just like a Mars entry capsule would when it enters Mars. This blunt end provides a lot of drag to slow down the vehicle at Mars. And this is shaped just like a Mars vehicle would be shaped, and is the same size as our Mars entry vehicle, so we can present the same environment to our devices that we would see at Mars. Then to get the right air density, we have to go up very high in our atmosphere, up to 180,000 feet. And we have to get it up going to Mach 4. That's what the big rocket motor is for. So this thing gets spun up. It accelerates up to Mach 4, and then from there, we deploy the side, which is packed tightly against the vehicle, a supersonic inflatable aerodynamic accelerator. It then inflates in a few tenths of a second and make a donut around the vehicle that's 20 feet in diameter to slow it down from about Mach 3. And then we deploy that ballute that Ian showed. It's the yellow ram air ballute that's being used to pull out the parachute at about Mach 2.9. Once that all slows down to about Mach 2.35, the parachute is pulled out of the pack, and at Mach 2.35, it's fully exposed to the flow. And at that point, the parachute then opens up and is able to do its mission, where we then observe the parachute in detail with the very high-resolution, powerful cameras we have in the vehicle. So this is the parachute cam where it gets pulled out of. These are the cameras over here that are looking straight up at the parachute. We have high-resolution, high-speed cameras, color stereo cameras to give us many different views of the parachute inflation and look at those detailed images and learn exactly what happened in that parachute inflation event through the supersonic flight and through subsonic flight. We also measure the trajectory very accurately, so we know how much the devices are slowing the system. We know what trajectory it followed, what density air it was in when it was doing it, and then we can reconstruct the aerodynamics of these devices, which then allows future missions to Mars to use all that data and simulate how these devices will work at Mars, so then they get great confidence that these things will work at Mars when they want to put their expensive missions on these parachutes and inflatable decelerators. So let me put up the next slide here and show you what the overall mission looks like here out of Kauai. So you see, it's just as a schematic. We launch from the PMRF base, just a little bit north of here, a large 34 million cubic foot helium balloon. This is a helium balloon that's a standard balloon that's used for launching scientific missions. This is normally used for astrophysics missions, where you put telescopes high in the atmosphere to be able to look into space. We're using it to launch our 7,000-pound test vehicle. We get it up to, with the balloon, 120,000 feet, most of the way to where we need to be. Once we get up to that altitude and we're in a good position over the ocean, we then drop the test vehicle. Within a few tenths of a second, spin motors fire to spin up the test vehicle. We then fire the main rocket motor to accelerate it. In over 71 seconds, it will accelerate from 0 to Mach 4. And by that time, it's also now going at about 180,000 feet above the surface, where the air is about the right density where these devices will be used at Mars. Once we're going Mach 4 at 180,000 feet, we can now deploy the devices, observe their operation, and test them. It's going roughly horizontally to give us a lot of time at condition. And then we then slow the vehicle down on the SIAD, then on the parachute, and eventually the vehicle arcs over on the parachute, and that same test parachute is also used to land the vehicle in the water. It lands out in the ocean, and we send out recovery ships to get it, which I'll show you in a second here. So let's show the Google Earth animation from last year. So this shows the PMRF base, and we show our launch site there, just south of the runway here at PMRF. That blue track is the ascent of the balloon. It goes over the island a little bit and then departs out across into the ocean. As the blue line continues, we allow it to get up to altitude. We had to wait for it to get up to about 2 hours for it to get up to 120,000 feet. At the end of the blue line is float. That red line is when we drop it and fire the vehicle, and then goes up high in altitude to actually up to about 200,000 feet in that test. It then conducted the test, and then it arced over, landed in the ocean. And on the next slide, after it landed, we sent out a recovery boat, and there's the vehicle after the mission being picked up out of the water. You see the side hanging on the side. We also recovered the parachute. We recovered the balloon. We recovered everything. We got all of our data back. Our high-speed video and high-resolution video all are on recorders on the vehicle. They're not telemetered down, so we need to get the vehicle or at least the recorder in order to get all that data. That was all successful last year, and that's exactly what we're going to do again this year. I mean, I'd like to thank, again, Captain Hay and PMRF. This is really a unique facility for us to be able to do this test. There's really no other place in the world we could find where we had the right conditions to be able to launch a balloon, to have it go out away from populated areas, to have support services here at the range, all the communications, the instrumentation that Captain Hay mentioned, to provide support for the mission, get our data back, do the operations. So now I'll show you a little bit of the balloon here. This is a scale model of the balloon. It's about 8 feet in diameter, and standing next to it is Petty Officer Quinlan. It's just to give you some scale. The actual balloon is over 400 feet in diameter, and in fact, our 15-foot test vehicle is about the size of a coffee cup lid. If Petty Officer Quinlan, if you can hold out the coffee cup lid next to the balloon there, so you can see how the size, how small that is compared to the balloon. So it's a very, very large balloon. It would settle very nicely into the Rose Bowl, carrying the vehicle up to the high altitude, being able to carry 7,000 pounds to altitude. Again, I'd like to thank also the Wallops Flight Facility and the Columbia Scientific Balloon Facility for providing this tremendous capability to allow our vehicle to get up to altitude and make this a very cost-effective approach to testing these technologies in Mars conditions. So with that, I guess I'll turn it back over to Kim for questions.
Thank you, Mark. Now we'll turn it over to questions. First, we'll go to reporters here in the audience. Then we'll go to reporters on the telephone. If you're on the telephone, please hit *1 to get into the question queue. And then we'll go to social media. So for questions in the audience, please raise your hand and we'll get a mic over to you and state your name and media affiliation. Any here from reporters? Right here in the front, Keith.
I'm Chuck Lasker with Social Kauai, and I guess my question is, with all this technology, in your opinion, how soon do you think we're going to put humans on Mars?
To put humans on Mars in the 2030s. And so we're developing a suite of EDL technologies to land larger masses at higher elevations to access more of the planet, like Ian said. But we need a whole host of other technologies. We need advanced in-space propulsion technologies to shorten the trip time. We need environmental control and life support system technologies that are more efficient so that astronauts can survive the trip. And then we need systems on the surface of Mars that can produce things like fuel and oxygen, and so we can kind of live off the land because we're not going to be able to take everything with us. So it's going to take a couple of decades to develop all that technology. EDL technologies are critical to making that happen, and LDSD is a really great advancement in EDL technology.
Okay. Next, we have a question from our telephone bridge, Irene Klotz from Reuters. Irene?
Thanks, Kim. I have a couple questions. The first, I think, is for Mark. Did I hear you say correctly that the diameter of the SIAD for this flight is larger, 26 feet, or were you just referring to the ground test that you did on that rail track? And I have another question as well.
Okay, so for the first one, that was a 26-foot diameter SIAD is not the one that we're flying this year. We hope to fly that on a future flight. The one that we're flying this year is 20 feet in diameter. It's like the one we flew last year, and we need that to present the right environment for the parachute test.
And then I guess on that note, I don't know who it was who referenced that with the successful deployment of the SIAD last year that this is now flight qualified for Mars, and someone else had said that with the parachute test could be ready to be tested on Mars as early as the Mars 2020 rover. And just wanted to know, I mean, obviously you don't need the extra mass on that payload, but is NASA actually considering using either of these systems on the Mars 2020 rover delivery? Thanks.
Right. So at this time, the Mars 2020 mission design doesn't require the new technologies. In fact, it was designed exactly in that way because they didn't know, and they still don't know, whether or not we're going to succeed in our technology development, and they have to proceed with the designs of their systems. And so we'll wait to see after we complete our technology development if there's some reason that they might consider to need them, but right now it is not the plan for 2020 to use or acquire these technologies. So the next opportunity we expect will be for components of Mars sample return, which in fact 2020 is beginning. 2020 will be collecting samples that we hope to eventually return to Earth. And to do that, we have to put rockets down on the surface of Mars that can launch these samples into Mars orbit. Those could be very large systems, and they very well may require the SIAD and parachute in order to get that system down to the ground, as well as other future Mars exploration, and as Steve alluded to providing cargo or other services to astronauts on the surface. And again, these also provide the first steps in a many-step program for trying to get to the point where we can actually have a journey to Mars with humans.
Thank you, Mark. Next, we have Alan Boyle with NBC News. Alan?
Hi, can you hear me?
Yes.
Okay, great. I may have missed some of the presentation, but I wanted to just double check on the weather outlook. I know last year there was quite a delay because of the winds. What's the outlook and what's the window in case you do have to delay the initial attempt? Thank you.
Right. So, in fact, as you were referring to, last year, our first 2-week launch period, very much like this year's 2-week launch period, we were not able to launch. We had wind conditions that prevented launch because we were not having the right trajectories to carry the vehicle off the island and away from populated areas to make it safe. And so, of course, we'll only launch if it's safe. And so this year, again, we're going to be looking at, for these first 2 weeks, for a possible launch opportunity. Right now, the outlook actually isn't looking too bad. I'm hopeful that by the end of the week or early next week, we will have a good opportunity. Right now, tomorrow isn't looking so great, but we're going to continue to watch the weather. It can change quickly. If we don't get off in these first 2 weeks, we do, in fact, have a backup period in July, from July 7th to 17th, that we could try and get off on, and where there might be better conditions. In fact, that's exactly what we did last year. We didn't get off in the first launch period, and so a couple weeks later, we came back and launched on the very first day of the next backup opportunity.
Okay, do we have any more questions here at PMRF? Reporters here. Raise your hand if you have a question. Anybody else here? Okay, now we'll go to social. Can we get a mic over here?
Hi, actually I have a couple. So starting from Twitter, the first one is, how will LDSD be controlled?
Controlled.
It's not actively controlled, actually. We use physics to control the vehicle. We point it in the direction that we want the vehicle to travel, and we use gyroscopic stability to help stabilize it and maintain it pointed. So in the sense, the vehicle is controlled by thrust, drag, gravity, and angular momentum.
And then also on Twitter, I have another one. How come aerodynamic surfaces are smooth rather than dimpled like a golf ball?
It depends on what you're trying to do with the aerodynamic surface. In the case of dimples on a golf ball, generally that's to help keep the boundary layer attached and have the golf ball fly in a particular way. For our aerodynamic surfaces, we are focused on trying to produce drag. Generally that means having very large, blunt surfaces that face the wind to create that drag, or creating geometries like parachutes where you have a giant bowl that's helping capture and slow down and create drag that way.
And then from Facebook, we have a question. What is the height of the drop of LDSD?
So it's dropped from 119 to 120,000 feet. It drops for about 100 or 200 feet, and then it accelerates upwards from there to 180 to 200,000 feet.
Okay. Okay, and I have one more from Ustream. What are the G-forces on the system when it opens up at Mach 4?
In the case of the SIAD, generally when we inflate last year and when we inflate this year, it'll be on the order of 3 to 4 Gs during the initial deployment. A lot of that, though, is because of the test vehicle that we have is relatively lightweight, even though it's full scale, because we're constrained in terms of how much mass we can take to an altitude. It's about 1/3 the mass of an equivalent Mars entry vehicle. So the G-forces are a lot higher for this test than they otherwise would be at Mars.
Great questions from social. And remember, if you're following us on social, use the hashtag #AskNASA so we can get you in the queue, and that's on Ustream and Twitter. Next, we'd like to go back to the phone bridge. We have Irene Klotz. Irene?
Thanks. I don't recall from last year what the time frame is for when a decision would be made about whether an attempt to conduct the test tomorrow would take place.
So we have opportunities every day to try and launch from June 2nd to June 12th. We decide the day before of a launch attempt whether or not we have good conditions. So we actually have a noon meeting on the day before a launch day to go through the conditions, the weather conditions, the safety calculations to determine if it's good. We will then, if the conditions do look good, we'll proceed with the launch. The folk will come in the evening. The INT team will come in at around 10 in the evening to start getting the vehicle prepared, roll it out to the pad, and start preparing it on the pad. A lot of the crew comes in then over the morning, 2 in the morning, 4 in the morning to fill out the operations team. And then we prepare for a launch that's going to be between about 7:30 and 8 in the morning most likely. Then the vehicle will launch from at that time and go up to altitude over about 2 hours. Then we might wait an hour or two to get to a good position to float and then drop and fire the vehicle. Now there is a chance that we could be a go for a launch the day before, but then later in the evening or early that morning we may determine that the wind conditions, the onshore breezes are not appropriate for a balloon launch, and we may have to scrub at that time and then recycle and then come back and have again another noon meeting that day to see if the next day will be a good launch day.
Okay, next we have Bill Harwood with CBS News. Bill? Okay, keep going.
Sorry, Bill Harwood. Can you hear me
gotcha.
now?
Yeah, we got you. Thanks.
Oh, I apologize, guys. I'm on a cell phone. Hey, I know you all told us this last year, and I may have missed it earlier today, but could you review the cost of the whole project, I guess, with the flight last year, this one, and what you guys have planned? Thanks.
So the total run-out cost of LDSD is approximately $230 million with our current manifest of launches in 2014, 2015, and 2016.
Okay, any other calls on the line? Any other calls here at PMRF? Social? I have one that came in from, let me see here. Peter King asked what is the weather forecast for tomorrow for the launch attempt? I think you might have covered part of that.
Yeah, so we are looking at the weather every day for the next several days. We're watching it very intently, though it's difficult to make predictions over many days. Right now, tomorrow is not looking particularly favorable. We are still going to go through all the process tomorrow and give it a shot. Right now, I'm hopeful that by the end of the week or early next week, we'll have some better opportunities.
Okay.
Mark's been honing his skills as a weather forecaster quite a bit lately.
So if we have no further questions, this concludes today's pre-launch LDSD mission briefing. You can follow us on www.nasa.gov/LDSD for mission updates. And thank you for joining us today.